All right, here we've got Praxis 5169 Algebra Set 1 Problem 6. It's about direct variation or indirect variation. Direct variation or inverse variation. I hope you'll see that inverse, invert, invertible fraction, invertible function, you'll eventually sort of feel automatically that inverse has something to do with backwards or reciprocal. And that's exactly what's going on here, the reciprocal uh, variation. Let's get direct variation though. Direct variation, the variation part means one changes with the other, and the direct means it's just a multiple. So a direct variation relationship has to be of the format y equals kx. K is some number. Let's say it's 7, right? So y equals 7x, that's a direct variation because when x changes, let's say from 0 to 10, right? Multiply by k, y changes from 0 to 70. If x goes up 10, y goes up 70. X increases from 10 to 15, that's an increase of 5, then y will increase 35, 7 times the 5 that x increased. So it's just, basically it's just a scale multiple. Y and x are in perfect scale with each other by that k, that multiple. So let's try to find the direct variations, right? I'll use red to, right? Y equals 3x is a direct variation, but minus 5 means nope, that's not a direct variation because you're not always going to triple. It's just not going to happen. Zero, when you put in 0, you don't get 0, so can't be a direct variation, right? There's too much here. B, too complicated looking. C, complicated. D, exponential function. E, oh good, that is, right? I mean, clearly you would need to, if you wanted to be picky about it, you should rewrite it as y equals -1/5, right? There's your k times x. But it's good enough to know that, y is a -5 multiple of x. X and y are directly proportional if they're multiples of each other. So this one's good. And nope, not that one. Too complicated here. So direct variations are easy to find. They're essentially linear equations with a 0 intercept, right? You're not allowed to have, right? You're not allowed to have a y-intercept. You've got to be a graph. Can't do here, right? But you can do any kind of graph through the origin, right? Anything through the origin, y equals slope times x will work. Inverse variation, all right? Inverse, the inverse, the reverse, the backwards, the reciprocal. That's what the word inverse is trying to get to you. Invert the x. Inverse variations means invert the x. So an inverse relationship looks like y equals, there's still some constant, right? But now it's not x, it's 1 over x, right? So we're taking that k and we're multiplying it by the 1 over x. In other words, as x grows large, well, 1 over x is a fraction. As the bottom of a fraction increases, as the bottom increases of a fraction, the total fraction decreases. So as x grows large, y grows small. If we just pick k equals 1, sort of the basic inverse relationship looks like y equals 1 over x. So the basic inverse relationship is the graph of 1 over x. You've probably seen it. It looks like, whoops, sorry, it doesn't touch, right? It's got the horizontal asymptote and the vertical asymptote. That's the basic um, inverse relationship. Now that can actually be a k, right? There can actually be a k. So really all the k does is scales it up by a multiple, stretches it up by a multiple, or squishes it down by a multiple. So just look for that shape if you've got graphs. If you don't have a shape, just look for y equals k over x. And I would like you to notice that y equals k over x is the same as xy equals constant, right? I just cross multiplied. I multiplied both sides by x to clear it out. So anything that looks like y equals constant over x or xy equals k, and of course, you could divide by y and, x equals k over y, right? So anything that looks like any of those is going to be an inverse relationship. The basic one that we always can try to aim for is if you want to solve for y, you better have k over x. So let's take a look now. We can see over there for b, look at that. It is that xy equals k format, right? Xy equals -4, right? The negative shouldn't phase you. If you wanted to be careful, you could solve for y. Y would equal the constant -4, right? And then there'd be 1 over x, right? So that would be the classical format of it, but you can recognize it as xy equals constant. So that's inverse, right? What about this one? C? C is very, very interesting. It has an inverse relationship, right? But it's not that direct inverse relationship. Sorry, bad language. There is some kind of inverse because as x grows large, well, x squared grows larger and the fraction grows smaller. I'm not sure you'll have to deal with this for the praxis, but I will mention that relationship is inverse square variation. That means the variable x, right, is squared and then inverted, put on in the bottom of a fraction. So that could be called an inverse square variation. I'm not sure you need to know that vocabulary for the praxis, but just in case, right? It's not inverse variation. It's a special kind of adjective inverse variation. So we would say no, but I would want you to realize that it's the inverse square variation. D, 2/3 to the power x. I mean, that has nothing to do with xy equals k, right? Power x, you'd have to take the xth root to solve, right? That's just no way. That's a completely different kind of function. And F, oh, that's just, that kind. You could swap the x and y, you could cross multiply, solve for the y, but we saw by exploring the original format, there's two other equivalent formats for an inverse relationship. So that is an inverse relationship, yes. So the idea for inverse variation, not as hard as it feels. It's just y equals k times 1 over x. There's the invert of the regular variable. Direct variation, y equals kx. Y is a constant times the variable. The other one, y is a constant times the inverted variable, right? Think of x over 1, invert it, you get 1 over x. And that's the thinking for the language used for inverse variation.